we're going to talk about heat and changes of state. Now, what do we mean by change of state? We mean when an object either absorbs thermal energy or releases thermal energy, and in doing so changes from a solid to a liquid, or liquid to solid, or from a liquid to a gas, or from a gas to a liquid. So it's changing state. So now first let's review a little bit. Okay, we've talked already about heat. That is the flow of thermal energy, the flow of the jiggliness of molecules. And we have this equation that describes what's happening. Now, really what's happening here is you might have a material. Okay, let's put, here's like a hot plate or something like this. And, okay, and on that hot plate we're going to put some block of metal or something like that. And what it is that we have heat flowing into this material. Okay, now what happens to that material as heat flows into it? As this amount of energy in joules is transferred into the object, well, what happens to the object? It changes temperature. It increases in temperature. We're adding thermal energy to it, and it increases in temperature. Okay, but there are situations where I add thermal energy to a system and the temperature doesn't change. And that's what we're going to talk about today. For example, if this was a block of ice that I took out of a really deep freezer, like really super cold, like negative 30 degrees Celsius, really cold, and I put it on like a hot plate, well, you might say, oh, well, it's going to melt. Well, no, it's not going to melt. It's not going to melt until it reaches a certain temperature. So heat will flow into it and raise its temperature. But then when you get to a certain temperature, 0 degrees Celsius, then it will start to melt. And during the melting process, the temperature will stay constant. And that's what we're going to talk about right now. So let's first talk about the heat. It's called the heat of fusion. Okay, now in your everyday life, you go to some fast food restaurant and you get a drink. Now it's a hot summer day, so here's your drink. Got a lid on it, got a straw, it goes into it. But what do you put in there to keep your drink cold? You put in a bunch of ice cubes. Right? You put in ice. Now ice is one of those rare substances that when it's in when water is in its solid form, it floats. Its density is less than when it's in its liquid form. That's really a wonderful thing about water, by the way. The earth would be inhospitable to life if ice didn't float. Okay. We'd be a big ice ball, is what would happen. Anyway, so here's our drink, which is mostly water, and with sugar or artificial sweeteners and a few flavors or whatever are floating in that water. Now, what happens is that you have a temperature difference. In your drink, it's 0 degrees Celsius. But maybe outside, if you go outside and maybe it's on a warm day, maybe it's 30 degrees Celsius. That's actually fairly warm. Okay, not the hottest day like we get here in Clovis, but pretty warm. Well, what did we say before when there's a temperature difference? Whenever in nature you have a temperature difference, thermal energy flows, and it flows from a high temperature to a low temperature. Okay, so what's going to happen is heat is from the outside environment is going to flow into this drink. Okay, we got all kinds, and it's going to flow until what happens to your drink? Until it reaches thermal equilibrium, which means that it's at the same temperature. Now, at first, though, you know, as long as you've got ice in there, the temperature isn't going to change. Because what happens is that all this heat, what is the result of heating, of adding thermal energy to this ice water system? It melts the ice. It takes energy to melt ice. Now, let's take a look at a little tiny chunk of the ice cube. What it is, and I'm not going to draw this very accurately. An ice cube or a crystal of water is you have water molecules that are in some kind of array, and this is not exactly what they do, but and remember, water molecules look like little Mickey Mouse molecules. They're in this crystalline array. They're holding each other in place. Now they are moving, they are jiggling, but they're holding each other in place. Then, because of heat being added to the system, when you add enough jiggliness to one of these molecules, it will actually break free of the crystal, the water crystal. In other words, this molecule will take off, will break it off, but it takes energy to do that. So it takes energy to melt ice, to take it from this solid form into the liquid form. And so what happens when you have your drink with ice in it, because there's a temperature difference, you're adding thermal energy to your drink, but to keep it cold, you put ice in it because the ice keeps it cold, because we don't have a temperature change while the ice is melting. Okay, when it's changing state from a solid to a liquid, because it takes energy, it takes to break them away from these ice crystals. Now you do pay a price for it. I mean, what happens to your drink as the ice melts? It gets watered down, and so that can affect the flavor of it. And so, but usually in the summer, we're more concerned about the drink being cold than it being at, its full strength of flavor. Now, of course, if you just go to the refrigerator and get a can of soda, so here's my can of soda, and here's the the pop top thing. Okay, there's no ice in there. So what happens as the heat flows into the can? It immediately starts getting warmer. So usually when people take a drink out of the refrigerator, the idea, if you want to drink it cold, you have to drink it fairly quickly. But putting ice in it lets it last a while. Now, the energy it takes to melt a certain kind of material. Now, usually what we deal with is water. Water's a wonderful molecule. Water can exist as a solid, a liquid, and a gas at room temperature and pressure, and this allows weather to happen. I mean, it allows life on Earth to exist. Water is just a wonderful, wonderful substance. The heat of fusion is, I'll just write it up here, is the energy required to melt 1 kilogram of a particular substance. Okay? So it's really a measure of energy. It's a measure of heat energy you have to add to melt substance. So Q. Now what is the heat of fusion for, well, so here's the heat you have to, here's the heat you have to add to melt a kilogram. So here's the mass of, well, that's the 1 kilogram. And then we have this H sub F. Now this is the variable that we use to describe the heat of fusion. So here's the heat, here's the thermal energy we transfer into the material. That will be equal to the mass of material that gets melted times this heat of fusion. Now remember, there's no temperature change here. There's no delta T in this equation. So I can solve for this heat of fusion. H sub F is equal to the heat that I added divided by the mass that actually got melted. Okay? And for water, the heat of fusion for water, which is really a high amount, is 33,400, that's 3 significant figures, joules of energy required to melt 1 kilogram of mass. And the heat of fusion will always have units of joules per kilogram. The amount of energy that needs to be transferred to melt a kilogram of that substance. Now that's if I'm adding heat to it. But what if I, do any of you ever, like you take a 1 liter bottle, like, here's a, not quite 1 liter, it's about half a liter, but here's a water bottle. And you fill it with water, and then you put it in the freezer, right? Because you want to have it for the day, you want to have ice water for the day. And so you put it in the freezer. Well, what has to happen there? It's just the opposite process. Let's suppose I put that, you have a bottled water here, and you put that, maybe it's a 2 liter bottle or 1 liter bottle, whatever, and you put it in the freezer, and you're going to freeze it. Well, let's say it was really cold to begin with. Let's say you get it down to 0 degrees Celsius, and then what happens is this, that the molecules in there, and by the way, try this, take a bottle of water, put it in the freezer, and check it every hour. And you can actually watch the water crystals grow, the ice crystals grow in the water until the whole thing is frozen solid. But what happens is that these molecules, I'll just draw a few of them in here, are all moving at a certain average velocity. They're at a certain temperature, okay? But remember, some of them are moving faster than others. And they're also, if this is like, let's say your refrigerator is at negative 10 degrees Celsius. Usually it's about -5. I'll just make it -10. And then this is at 0 degrees Celsius. What's in here? Well, heat flows from low to high temperature, right? So heat is going to flow out of the bottle. There's Q, there's Q, there's Q. Well, because it's until this reaches 0 degrees Celsius. Well, but at first, the heat doesn't change the temperature. What happens is that, well, it does. If you put it in there, it's at room temperature, right? So it's like 25 degrees Celsius. So at first, it's got to get down to 0 degrees Celsius. But now let's look at it, now that it's at 0 degrees Celsius, let's take a look at the water molecules. What do? Well, the ones that are moving slow enough, like let's take a look at these two. Well, I'll just draw another one. These two right here. On average, they're moving slower than the others. Remember, the water molecules are moving at a lot of different speeds, but their average speed gives them a temperature of 0 degrees Celsius. Well, these are at a low enough rate of speed where they can actually stick together. And what they do is they hook together and form a little tiny ice crystal. But what that does is that when these two hook themselves up as an ice crystal, that leaves these guys at a higher average speed. And so that will, but they will eventually lose their velocity because their thermal energy gets transferred to the outside environment in the freezer, thus lowering their temperature. So this one loses its speed, and now it hooks up to the ice crystal. And then more heat flows out, and this one loses its speed and hooks up to the ice crystal. And then this one loses enough speed to hook up to the ice crystal. And so what happens is that slowly over time, the molecules will move slow enough to hook themselves up to that ice crystal and grow the ice crystal. But the water molecules around them are still at an average speed where they're at 0 degrees Celsius. And that heat has to transfer to the outer environment in order to slow them down enough so that they can hook up with the other water molecules in the ice crystal. Okay, and this takes time. You know, if you ever notice, you put an ice cube tray in your freezer and you're out of ice and you want ice and it seems like it takes forever. Well, it takes a few hours. This takes a few hours to do. In a typical, now, if you want it to happen really, really fast, what if you wanted, man, I want an ice cube right now. I want a microwave oven for ice cubes. I want to be able to stick that ice cube tray in there and boom, take that thermal energy out. What do you have to have? You have to have a super freezer. You have to have this at a much lower temperature. The rate at which heat will flow depends on the temperature difference. You have a huge temperature difference, the heat will flow very quickly. And they do have freezers that are really, really cold. And they can, like I was up in Alaska a few years ago doing some fishing, and we caught a halibut. And so we took it to this place, and we cut up and had all our halibut steaks ready to go, but we wanted to ship them back to Fresno. And so what they do is they flash freeze it, and they have this freezer. They call it flash freezing. It does take a little bit of time, but they put it in a freezer that's really, really cold. I don't know how cold it is, but it's really cold. And in a matter of minutes, it's frozen solid. And then they wrap it up, put it in a ice chest, and ship it. And it stays cold. So, but that's the process. So the heat of fusion not only is the amount of energy, see here, we're melting the ice, and the heat is flowing into the ice and thus breaking apart the molecules, and we're changing state from a solid to a liquid. But we can do just the opposite here. If the outside temperature is less, the heat will flow out, leaving the average motion of the molecules slow enough where they can start reassembling themselves into ice crystals. And that's a change of state. And for water, this is how much energy you need to transfer out of it or into it to change a kilogram from a solid to a liquid, or a liquid to a solid, right? From liquid water to ice, or from ice to liquid. See, if heat's flowing in, you're going to melt it. If heat's flowing out, you're going to freeze it. Okay? So it's the same kind of deal. Now, if you get the temperature of water hot enough, you get what's called the heat of vaporization. And I think you can kind of see what's going on here. Heat of vaporization. We call that H sub V. And it's really the energy transferred, from the environment or into the environment to boil 1 kilogram of substance. Now I'm talking about boiling, but what's the opposite of boiling? Anybody know what the opposite of boiling? Boiling is when you go from a liquid to a gas. What do you call it when you go from a gas to a liquid? Yeah, condensation, that's right, condensation. And by the way, you don't need to boil it. You could just let it evaporate. We'll talk about evaporation. It's the same basic process. Heat transferred to boil 1 kilogram of substance. Joules per kilogram. Okay. So suppose I've got my hot plate here again. And I've got a beaker on here. And this is, you know, just like what happens at home on the stove. And you've got just water in there. And we're gonna transfer heat. See, this is really hot. This is probably like 800 or 900 degrees Celsius. You know, this, and you know, this, so it's really hot. So it's going to transfer heat into the water very rapidly. And what happens if you look at the individual water molecules? Let's take a look at this. Let's blow this up. So here's the surface of the water. So here are the water molecules. Now we've increased their temperature, right? You've got to increase the temperature before the water will start to boil. And for water, it turns out that the hottest you can get it is 100 degrees Celsius at, you know, at sea level in an open pot. So these water molecules are moving really, really fast. Okay, they're on average. Some of them are moving slower than others, but some of them are moving really fast. Now, what happens here, the reason why water boils is that you'll get some water molecules that are moving so fast that they break away from all the other water molecules. Okay, see, water molecules are moving fast enough where they can't align themselves into a crystal. Let me zoom all the way out here. The water molecules, when they're frozen, they hold each other in place. They jiggle, but they hold each other in place. And then when they're a liquid, they can slip around each other. They're moving fast enough where they can't hold each other in place anymore, but they can slip around. And then every once in a while, one of them will go so fast that poof, it just takes off. So these are as fast, these molecules are moving as fast as they can move and still be stuck together. But every once in a while, one of them hits another one and gives it that extra jolt that it needs to, boom, take off into the environment. Now, that was a really fast-moving one that left, leaving the average a little tiny bit lower. But we keep adding heat to it from the hot plate. We keep adding heat to it until one of the other ones gets a higher velocity than it can have and still stick with all the others. And so, boom, it takes off. And boom, it takes off. Okay, so what happens is that the water molecules are leaving the liquid, and you're actually vaporizing it. Now, how much energy does it take to do this to 1 kilogram of water? Okay, well, the heat of vaporization of water, it turns out to be really a lot. 2,260,000 joules of energy to boil away 1 kilogram of water. So here I've got a couple of water bottles. Here's this is just over half a. I shouldn't advertise. Okay, this is just over half a liter. So if I wanted to put this on the stove and boil it away so that it's gone, well, it's not gone. What is it? It's now a vapor in the air. If I wanted to boil this much away, well, it would take about half that much, or 1,130,000 joules. So this water bottle right here, this water bottle takes over 1 million joules of energy to vaporize it. Now that's after I already got it to 100 degrees Celsius. So I got to put energy into it to increase its temperature to 100 degrees Celsius, and then I got to put 1 million joules into it to get it to boil away. Okay? Now, that's a lot of energy, isn't it? That's a lot of energy. Now, if you've noticed that water, even, water will evaporate. you know, if I put, well, let's just do it. Go ahead and do it here. I'm going to put a little tiny bit of water on my hand. Okay, well, let's see. I already spilled some on my notes. Okay. So here's some water in my hand, and I'm going to put it on the back of my hand here. Let me move my notes out of the way so I don't get wet. So I don't. Oh, yeah. Okay. So I'm rubbing it all over my arm. I'm spreading it out. Look at those big guns. All right. So I'm spreading it all out. Now, when you put water on your arm, let's say it's really, now today's kind of a cool day, but if it was a really hot day, you put water on your body. Why? Because what happens, especially if I blow on it? What do you feel? It feels cooler, doesn't it? Because water is evaporating. Now, evaporation is the same thing as boiling. It's just not as rapid. When you're at the boiling point, it means none of the water molecules can move any faster without turning into a vapor. But here, the average speed of the water molecules is quite, is pretty low. So most of it's going to stay at a liquid. But every once in a while, one of the water molecules, pow, it's going to get hit in such a way, it's going to get thermal energy transferred to it in such a way that it leaves. It evaporates. Now, almost all the water is gone. And so it takes energy to do that. And so this is why your body sweats. Okay? You sweat when your body gets too hot, and your body has these little things in there. I don't know if you can't really see them. There's zillions of them. Little sweat pores. And it's just liquid water that comes out of your body and spreads out over the surface. And as it evaporates, it takes heat energy away from your body. It could, because it takes energy to vaporize water. And so this is, this tells you how much. So the heat it takes to melt water or melt any solid, we call the heat of fusion. And it's equal to the mass of the substance you have times, well, I'm sorry. This is the heat it takes to melt this amount of stuff. And then this is the heat it takes to vaporize some stuff. And then here's the heat it takes to change the temperature of stuff. And then so you can use all three of these. Now these are really the three equations we're going to use the most in this unit. There's a couple other ones we'll get to later. And you just add it all up. Now let's say I've got an ice cube at, let's say it's negative 10 degrees Celsius. And I put this ice cube in a container, put that container on a hot plate, and I turn on the hot plate and I'm transferring heat into it, and I want to know how much heat do I need to boil away that ice cube. All the water in that ice cube is going to get boiled away. Well, what's the first thing that's going to happen to this ice cube? It's going to what? Change temperature. To what temperature? What temperature? Well, it's eventually going to get to 100 degrees Celsius, but before it gets to 100 degrees Celsius, it's got to get to what temperature? 0 degrees Celsius, so that it can do what? So that it can start to melt. So we're going to have, first thing we're going to do is do MC delta T, and that's going to be to raise the temperature to 0 degrees Celsius. Then we're going to add to that the heat it takes to melt it. And that's going to be the mass times the heat of fusion. Then, what do we need to do? If we're going to boil it away, is it going to start boiling? No. What temperature does it need to be to boil? Now, this is still at 0 degrees Celsius. It's melted, but when it finishes melting, it's still at 0 degrees Celsius. So we got to raise its temperature. Plus MC delta T again. And then, once it's at 100 degrees Celsius, we can boil it away. And so this is the amount of heat it's going to take to boil it away. So we have to add all those together. Now, of course, I need to know what mass it is. I'm running out of time here. So I would give you the mass, and I'd give you the initial temperature. But, hey, here's the thing you need to know. The specific heat of ice is not the same as the specific heat of water. So you need to look this up. And I don't have it here with me. I'd have to look it up. So this is for ice. This is for water. Okay, now there's going to be some problems where you have to figure this out. This temperature change, what is delta T here? Well, from negative 10 to 0, 0 minus negative 10 is 10 degrees Celsius. What's the temperature change here? We're going from 0 to 100 degrees. So that's 100 degrees Celsius. That's a much bigger temperature change. And the specific heat is greater. The specific heat of water is greater than the specific heat of ice. And then you have to look up these, which I gave you already. And then you have to add them all together. And that's how you're going to solve a lot of these problems on the homework. That is all.